Good morning. The miracle of technology. Good morning. I'm Frank Howley. I'm the Senior Director of Corporate Development here at the Baskin School of Engineering. I work for the Dean, and I work to get companies engaged with both our research and our programs like the Corporate Sponsored Senior Projects Program. Very pleased to introduce Mike Baker, who is from the first class of BSOE as an alum. And he is the VP of Software Development for Cativa, and he's going to talk to you about what it is they're doing and the project they've got for us this year.
Morning. So we did a project last year with the senior projects, and some students worked on a image capture system. This year we have a project where we could use your help with basically a motion control problem, looking at controlling vertical motion with pneumatics. Let me tell you a little bit about Cativa. So this long orange blob basically says that Cativa is part of the manufacturing industry that makes electronic devices. Mostly what we work on today are displays. Mobile displays and larger tablet and TV-sized displays using organic LED technology. So right now, in the last year or two, Cativa has basically made it possible to ramp mobile OLED production by providing a technical solution to a problem that there wasn't a solution for previously. And right now we're working on enabling the production of lower cost OLED televisions and larger displays. Closer. So some of you may not remember the CRT, but displays have moved lately from LCD and are moving rapidly towards organic LED. I'll tell you a little bit about the benefits of organic LED. It is cheaper. It can be made, the displays can be made flexible. With control of lighting from the individual pixels, you can have lower power, very thin displays. They're already quite thin, but they can go thinner. They can be shatterproof. They can be lighter and have much better picture quality. In order to make OLED displays, Cativa makes printers, large inkjet printers, like this is part of one. So this motion stage has three axes of motion control. The y-axis moves these large sheets of glass or plastic that the displays are mounted on underneath the inkjet print heads, which are mounted on the X and Z axes, which move them above the substrate. So the Z-axis is a little bit special in that it's fighting against gravity, and the weight of the printhead assembly can be quite substantial. So the fine motor control or fine motion control of this device is done with a linear motor, but we use air cylinders and pressure regulators to relieve some of the weight of that assembly so that we're not using a lot of current to hold it stationary, and when we do lose mechanical control, we can use pneumatic to push it away from the glass substrate and keep it from falling. So the objectives of our project this year is to build a test bed made up of an air cylinder, pressure regulator, maybe a small computer like a Raspberry Pi, air pump, and a spring to simulate the load in order to design a controller that's capable of holding position under a changing load. So adjust the pressure to keep the thing where it's supposed to be. Control the velocity of the Z-axis, in this case, when we want to move it, and to compensate for mechanical friction to smooth out the motion. So when you take control of something with a pneumatic lift like that, there's a lot of stiction, a lot of mechanical friction that doesn't want it to move at first, But once it lets loose, it really moves quickly. So it's a nonlinear control problem that we could use some help coming up with methods for controlling. So Cativa can provide a description of the project, the things we want to achieve. We can provide materials. We will have a few people who can meet regularly with the team, likely including a student who participated in this program last year. And then we're hoping to staff a team at the School of Engineering to build the test bed, design a position control and velocity control algorithm and implement it, and show us their progress. So basically what we're talking about is an air cylinder that's provided with pressurized gas through a pressure regulator with feedback from a position sensor. So the controller is going to adjust the pressure in order to, in this case, maintain position under a varying load. So the print head assembly that we put on this, the weight of it changes based on how many print heads there are, how much ink is loaded, where you are in the print process, but we're extremely sensitive to the position accuracy. How far away the print head is from the substrate affects the quality of the print. I'm sorry, I don't remember what this slide is meant to show you other than terminology of the inputs into this system. You've got a position signal from an encoder.
I could explain.
Sure.
For those of you that don't recognize this, this is a dynamic description of the derivative behavior versus time of the actuator. This is very important because there's a lot of mass. You can't move mass in zero time, and this becomes part of the nonlinear feedback control problem.
So essentially these will be some of the variables in your equation to solve this position problem. Compensating for mechanical friction. So the friction that exists or that is shown as the device is moving up or down is nonlinear, and controlling for it is a difficult problem. We have a couple of scenarios that we'd like to solve for, and one is after loading everything we need to load onto the printhead assembly, we need to quickly determine the right pressure to essentially hold that thing weightless on the motion axis. The other main use case or scenario is if we lose power to the electrical motors, we want the pneumatic system to take over and move the printhead assembly up and away from the substrate, preferably without slamming the whole thing into the hard stop, which is what it does today, which is a little tough on the printhead assembly. But controlling for position, speed, and acceleration, when you're faced with this stiction of when it's motionless and less friction as it's moving, we think will require a little bit of research and experimentation. So that's the gist of it. If you have any questions. Sure.
Is that getting on the recording? Yeah, if you repeat his question.
So you asked about the OLED manufacturing process. So I had a slide, but I think I took it out in interest of time. Essentially, the OLED manufacturing process involves depositing layers of materials, much like the semiconductor chip manufacturing process. For OLED, we work on two layers at Cativa. One is called an encapsulation layer, where the mobile display has been fabricated, and we want to protect it from moisture and oxygen. So we use a printer to print a thin, consistently thick layer of protective material. That allows the manufacturing not only of OLED displays, but also of flexible OLED displays, because the material can flex. And this is the enabling technology for some of the mobile displays that have gone on the market recently, where they're bent around the corners, or some of the prototypes you may have seen for folding displays or rolling displays. Being able to encapsulate that with a layer that is thick enough to protect it, but thin enough to bend and not be easily damaged is something that we're using inkjet technology for. The other application, which is maybe more to your point, is today's OLED television manufacturing process. They make an OLED backlight. So use organic LEDs to provide white light to the back, through the back of the TV, which is then filtered by an LCD panel, which is the same as every LCD TV has been for decades now. What we're doing with inkjet technology is printing the OLED materials directly into the subpixels, the red, green, and blue pixels, so that when you excite them with current, the subpixels themselves provide the light. There's no backlight, there's no filtering, you're not trying to block out white light to make black, you're not trying to filter white light to make red, green, or blue. So you don't need that LCD panel in front. You don't need a backlight. And you have illumination control at every pixel, actually at every subpixel, so that you can make totally black blacks, which is what everybody talks about with display technology, how dark the unlit area appears. High contrast, it's very thin, there are fewer layers. But that's the part of the current display manufacturing process that we're trying to attack. So the question is about kind of the technical aspects and whether there'll be programming or how much programming would be involved. I would expect in terms of programming, there might be some embedded programming required to implement the feedback cycles. So right, reading in the position sensor, controlling the pressure regulator. We're thinking a small embedded controller, probably programmed in C or C++, would be adequate for demonstrating different techniques for controlling position and velocity. Did I answer your question? Any more?
We had more hands up there earlier. Anybody else?
Is it on? Even I can hear that.
You look terrible, Ryan. Did you dress for the occasion?
I'm reading my amateur radio shirt.
We'll talk about professional dress codes later. It's a little early in the course.
Or lack thereof. Hi, guys. We're representative of the SlugSat.
This is being recorded.
Is it really?
Yes, it is. Now, here's how you talk in a mic, Ryan.
Okay, how do you?
Don't do this. Do this. Is that good?
No.
Is that better? Okay. About 2 centimeters.
2 centimeters. All right. All right, hi guys. We're part of the SlugSat Senior Design Project, continuing on from last year. I'm Ryan Vandenbleckert, and this is Kevin.
Yeah, I'm Kevin.
No last name, just Kevin.
It's not important. All right, so wait, where do I click to go to the next page?
The middle one, that's it.
It's not working.
That's because you press this.
Oh, sorry.
Hang on, we have to get the...
Yeah, I'm an EE, not a
IT.
not a PPT.
Okay.
Oh yeah, that's perfect.
Now,
So
it's this little button right here.
got it. Okay. So the first question is, what is SlugSat? So basically, what it is it's a miniature satellite that's meant to be used for communication. Next. And then it has 3 components to it. The first one is a CubeSat, and then the second one is a linear transponder, and then the third one is science. And you guys might not know what that means yet, but hopefully you will at the end of the presentation. So what it's meant to do is SlugSat enables the communication of licensed amateur radio operators within its footprint. And what a footprint is if you look at the image over there, a satellite, you can think of it as like a like a light, and then it'll project a ring onto the Earth. And if you're within the ring, the satellite will be on your sky, and if you're not within the ring on the Earth, the satellite will be below your horizon. So that's what a footprint means. And then I'll explain more later into the slide. And then next slide. And so why is it important? Amateur radio is actually your First Amendment. It's freedom of speech. And the example is in 1986 in Chernobyl. There was a little hiccup in the power plant, and it blew up. And obviously, a source of all evil in that era, the Russian government tried to cover it up. So the first news that came to the West was actually a transmission from a local amateur radio license operator. So basically, nothing can control you once you get the amateur radio because it's a direct connection. So if you're American, you better join our team. Amendment. And then this is our project motivations. Our primary customer is the amateur radio community, and what our goal is to we aim to install amateur radio linear transponder, and I'll talk about what that is, into a CubeSat. I'll also talk about what that is later. And then it's actually meant to be a pilot program that establishes a foundation for future UCSC students to work on space-related projects. So, next slide. And then what is a CubeSat? So it's basically the standard unit is 1U, and that's a 10 centimeter by 10 centimeter by 10 centimeter cube. That's about 1.33 kilograms. And where this comes from is when a rocket is launched, it's designed for a specific amount of weight on it, say 500 kilograms. And say when NASA designs a satellite, it's rarely exactly 500 kilograms. So what happened before was they put on basically dummy weights on there. And some student at Cal Poly came up with this genius idea that they can sell this space instead of putting, just iron on there or whatever weight to stabilize the rocket, they can sell that space to, get rich quick. So that's where the CubeSat came from. And then the price for 1U is about $100,000, but a lot of it's a launch cost. So what happens is we will get our design and pitch it to a space agency, whether that be NASA, Capoli, JPL, SpaceX, whatever, Russian. So, and then and then if they approve it, they'll pay for the launch costs. So that's how it works. And then next slide. And then so to give an idea of where the satellite orbits, it's actually in a low Earth orbit. And then the low Earth orbit is defined as anything under, I think, like 2,000 kilometers. And then CubeSat, so if you guys don't know how space orbits works, the height of the altitude of the orbit actually is basically equivalent to the velocity of the satellite because of how the science works. And if we launch at 450 kilometers, there's actually air resistance in low Earth orbit. It's not permanent. At 450 kilometers, the CubeSat will orbit around 1 year, and it will fall out of the sky. The orbit will decay. And at 650, which is higher, it will orbit for around 25 years. And NASA actually was not happy about how many CubeSats stopped working, and they still left in orbit. So now they're launching it, for NASA, they're launching it about 5 to 10 years. That's what we're looking at, the time frame. So once it's launched, it will stay in it for that long. And just to give a perspective, you can click one more time. The ISS is around 420 kilometers, which is lower, but the ISS doesn't decay because it burns. And the GPS satellite is about 20,000 kilometers. So, yeah. And then here are some examples of the launch opportunities, which I'm not going to go into. You guys can look at it. It's just, as I said before, we just apply to different space agencies. And then next slide. Oh, go back. So here is an example of what could be on a CubeSat. There are a lot of different areas you can work on. There's mechanical stuff, there's secondary payload, there's CubeSat control, magnetic, solar panels, that's not me. And then there are many online resources available. So if you're interested in any of those fields, it's a good idea. And any of them can be expanded. So like say solar panels, you can like design your own solar panel if you wanted, like from scratch, if you want to work with silicon wafers. That could be a possibility. Or we can just buy it from, because a lot of it is also commercially available, which also means there's a lot of online resources that you can look up if you get stuck. So you also get a killer resume entry if we finish. So that's the goal, But the next question is, since there's so many satellites getting launched, what's so special about the SlugSat? Why are we special? Why would someone pick us over, someone else? Next slide. So our primary payload is the linear transponder, which is the part that enables amateur radio communication. And this diagram is actually wrong. So, but it gives you an idea. I was going to fix it, but I didn't. Yeah. But so you have an input frequency and an output frequency, and there will be a specific offset that linear transponder gives. And then next slide. You keep clicking. And then that's a specific offset. And then if you move the input frequency a little bit, you can click. The output frequency also moves in correspondence. So that's basically what the linear transponder does. And there's some problem with this diagram, but that gives you an idea of what it does. And next. So where in the electromagnetic spectrum we're talking about? We're talking about the radio frequency spectrum. And then as a reference, the red circle is where the visible light spectrum is. So it's towards that. And then next slide. And then this picture shows, colored of the same thing, basically. And normally, satellite communication is done at the higher frequency end, the very high frequency, ultra high frequency, and S super high frequency. But our satellite is in the HF high frequency range, which is near the radio part. And why is so? Next slide. So normally when you have satellite, you have to point your satellite dish or your antenna at the satellite as it goes across the sky. And you have to track the movement of the satellite on top of Doppler shift and like, Lorentz transformation and all that. But because of the structure of the HF antenna, we actually don't have to aim it at all. As long as you're within the footprint, you can communicate with the satellite. And sometimes if you're outside the footprint, you can also communicate with the satellite. And I'll talk about that in the scientific payload. But some people might ask, like, what's the difference between, since you don't have to point your cell phone, you don't have to point the cell tower to talk on your cell phone, what's the difference? The difference is cell phones, you actually need like an infrastructure. You need cell towers and stuff. With amateur radio, you only need whatever gear you need, and the other person have their gear, and you don't need any cell towers. The example would be in Puerto Rico when they got swarmed by the hurricane. All of their cell towers went down, and the Red Cross actually called for amateur radio operators to help them relay information because there was no infrastructure in place. And also, you can't just call ISS to talk to a satellite. To talk to an astronaut, unless you know that number, in which case you should give it to me. But that's not the point. And the next slide. So actually, if you want to know detailed information about the HF propagation and stuff, Professor Peterson will give us a talk at the amateur radio meeting this Wednesday at 6. He'll talk about how satellite communicate with ground stations and how HF propagates. So and plus, if you want to work on a project, you're going to need a license eventually, so might as well start early.
Yeah, but didn't I give that talk last week?
No, the HF propagation. I thought you, it's okay. Next.
We talked about satellite communications at the last meeting. Do you want me to repeat that?
No, I thought you were going to say something related to that.
Yeah, it's fun, but that's about all I can add.
Yeah, sure. We'll figure out the details at the meeting. So with HF, normally with higher frequencies, the waves just go through the atmosphere. With HF, there's actually an angle that the radio frequency will go through the atmosphere, and under that, bouncing. It'll start bouncing around. And this is pretty well documented, but there's other factors that affects it, like the sun cycle and the weather and all that time of the day. So what our scientific payload could be next is we can document this, and they just basically need more data. There's not enough satellite in space right now to give us information about exactly when it's deflected and exactly when it goes through. So, and the advantage of this is we can actually do all the data collection on the ground. So I don't think any extra hardware needs to be implemented on the satellite, but we can talk about that in the team meeting. So, and then so here's an example of what the project was started last year by a group of seniors. This is what they came up with, and that's actually just a primary payload. That's just a communication section, and they did not even finish because there were actually a lot of factors that might affect it. An example would be like if you do a quick Google search about what the temperature differential is on the dark side and light side of orbit, it's about like -200 Celsius on the dark side and +200 on the sun side. But actually, Capaldi launched a CubeSat that only had 2 temperature sensors on there, one on the inside and one on the outside. And then they documented the temperature difference is 30 degrees on the sun side and -5 on the dark side inside the satellite. So why is that? It's because there's no way for heat to dissipate in space because it's vacuum. So you only dissipate through radio waves. That's what I got out of the paper anyways. So there's a lot of stuff to consider. Like the temperature standard for the industry is -40 degrees Celsius to +85 degrees. So would that work for our satellite, or do we have to calculate the heat within our satellite to keep our component at that temperature? So it's a lot of work. And yeah, next. That's the example. Oh, nah. And then, so right now our goal, our number 1 priority is to form a team and figure out what the team want to do with our CubeSat, because there's a lot of opportunities and everybody have to agree on a design. Like the simplest design would be we put a linear transponder on there and we put power system in and we just launch it without carrying anything. But then who would pay for that? You know. So there's trade-off studies that we have to consider, and we have to agree on a charter. And then we'll have to finish the linear transponder from the previous year and do some stuff, and then build the satellite and launch it. It's might be a lot of stuff, but you know, it's okay. And then who are we looking for? We are basically looking for everybody, and the thing is, whoever joins the team has to justify their role on the team. So if there's anything that you are interested in any of the systems, you can talk to us and we can try to fit you in onto the program. But it's a democracy, right? Everybody have to agree. So come to our talks and we'll have to discuss it out. Yeah. And the next slide. And then the sponsor is Professor Peterson, amateur radio community, and then the temporary meeting time for the SlugSat team is on Tuesday and Thursdays at 4 p.m. And the ham radio meeting is Wednesdays at 6 p.m. And if you can't make any of them, you can email us at slugsat@gmail.com. That's it.
Are there any questions?
It's only the design of the linear transponder. There's still a few points on the design that still need to be consolidated, and then we'll still have to make the board. So, yeah. Yeah.
There's actually more than that. Kevin didn't quite get it right.
Let's take it.
Last year, the project was conceived by a team that realized there's a lot of different areas to this, so they decided to make it multi-year. Last year, there was more than the transponder design. There was also the choice of the form factor for the CubeSat. There was an engineer that looked at the antenna design for the 10-meter, 21-meter band, or 21 megahertz band that was going to be used. There was a lot of research that was done that came up with the specification for the frame. There's no power budget that's been done yet. And as Kevin and Ryan understand this correctly, the transponder is a conceptual design. Students have built pieces of it and actually made them work experimentally. It needs to be fully assembled, tested, and verified. The design will probably also change to some degree.
Any other questions? Yeah.
No software testing.
There's software simulations, but there's no. I think they use Microwave Office for parts of it, and then PSpice for anything. Yeah. Any other questions?